Okay, friends. Today we'll start with one of the engineering subject, which belongs to the branch electronics and communication. Um, the subject name is digital communication, and the 2017 scheme it is in the sixth semester. So it has five modules. The first module is as shown here. It has two sections. One is band pass signal to equivalent low pass signal, and the second section is line codes. In the second module, we will come across signaling over AWGN channel, that is noisy channel. And in the third module, we are going to come across digital modulation techniques, as you already studied some analog modulation techniques in the principles of communication system. And the fourth one, that is the fourth module, you have the communication through a band limited channel. And the fifth one, which is called as principles of spread spectrum. So this is a brief introduction about your syllabus. So today I'm going to start with the first module, that is band pass signal to the equivalent low pass signal. So it contained the parts are Hilbert transform, pre-envelope, complex envelope, canonical representation of the bandpass signal, complex low-pass representation of a bandpass system, complex representation of a bandpass signals and systems. And in the second section, we're going to come across the line codes, unipolar, bipolar, Manchester code, and their power spectral densities, overview of some other codes, HDB3 and all those things. We'll see all those things. In the first section, what we want to do is, our aim is to convert our bandpass signal to its equivalent low pass signal. So to do that, we require one tool which is called as Hilbert transform. So first we want to learn this Hilbert transform. Using this tool, we're going to derive rest all part, that is pre-envelope, complex envelope, canonical. How can I represent the bandpass signal with respect to the low pass signals, and so on and so forth. So today in the lecture, we're going to start with the first one, that is Hilbert transform. So before starting the Hilbert transform, so let me take a brief things which you already studied. So I will take two sections. One is signals and the section is Fourier. Signals, I'm not going to in depth about what all the different types of signals, how can I categorize them. I'm just going to stick to the one category, that is periodic and non-periodic. The signal is divided, categorized as periodic and non-periodic. So as we know that for the periodic, we are going to apply the Fourier series, and for non-periodic, we are going to apply the Fourier transform. So this we know it. So again, I'm not going to go in depth about the Fourier series because it is nowhere related, and obviously you people will get scared whenever Fourier comes. But it's very easy. No need to scare about that particular Fourier series or a Fourier transform. So I'll not go in depth about the Fourier series. Let me start with the Fourier transform and just give the brief introduction of the Fourier transform. So Fourier transform, it is useful for evaluating the frequency content of a signal. So that's a definition, or it is also called as a frequency selectivity. But question arises, yeah, the definition is already written in the notes, what exactly it is. So what I'm doing is, in this Fourier transform, the signal will be there. So there will be signal. So this signal, as usual, this is mufti, I'll call all these things. I'm going to convert this signal into its spectrum. What do you mean a spectrum? It's a representation of this signal into the form where I can see the content, all the content of all frequency content in of the signal. So it may be here, if I see the frequency is low, if I go on seeing towards the end of the signal, the frequency is getting increase. So the different frequencies are present in this. So Spectrum means representing all these signals in a one diagram. So what it says that this particular signal has a frequency from minus W to W. This is what? Just a representation. I don't know, I'm not going to give what is the value of these things. Say it has from 1 to 10 hertz or 10 kilohertz, 1 hertz to 10 kilohertz frequency present in the signal, for example. So this will be from, if I go with this, if I convert this, so it will be having from 1 hertz, sorry, this is my 0 here. So from 1 hertz to 10 kilohertz. So all the frequency contents I'm just representing with a triangle shape. We can represent by parabola also, it's not a problem. So question arises, okay, it is going to show me the frequency content of the signal. And what I'm telling again, it is a frequency selectivity. That means in this, from this signal I can extract, this is just for show you what exactly it is. So I can extract different kinds of signals present, different signals of different frequencies present in this. So all these signals are present. By applying the Fourier transform, I am going to get these signals from this signal. So if I combine all these things, I'm going to get the original signal. So this is a brief introduction about the Fourier transform. Simple. It's going to show me all the frequency content of the signal. So when the frequency content of the signals are known, then it is very easy to go for the mathematical structure. Okay, after knowing brief thing about the Fourier transform, let me shift myself to the Hilbert transform where the syllabus gets started. So there are 4 points which you have to remember in the Hilbert transform. First thing, it does not involve in the change in a domain. What it means, if I look at other transforms, like I will take an example, that is Fourier transform, which you already studied. So this Fourier transform, what it does, it will convert the time domain into the frequency domain. And the next comes is ZT, that is Z transform. This also was studied. So this, what it does, it will convert the time domain signal into the Z. And another one which was studied is Laplace transform. What it does, it will convert the time domain into the Laplace domain. So the domain is getting changed in all these 3 which you already studied. But in the Hilbert transform, the domain is not going to change. Remember that in the Hilbert transform, the domain remains from time domain to time domain. Now question arises, if it is remaining from time domain to time domain, what is the need of doing it? The answer for this is, again I will go back to the previous 3 or only one I am going to explain. In the Fourier transform, we are going to convert the time domain signal to the frequency domain signal, and whatever the signal which you are in the time domain, it is being represented in the frequency domain. That means the signal what you see in here, it will be same signal will be present here, but only domain is getting changed. But in the Hilbert transform, it is not going to change the domain, but it is going to change signal itself. We'll see it how it is going to do it. As of now, just remember the first point, it is not going to change the domain. Previously it will be there in the time domain. After applying Hilbert transform, it will be there in the time domain itself. And the second one is the signal is getting changed in the Hilbert transform. But in the Fourier transform, the signal is not getting changed. The signal remains the same, only the domain getting changed. But in the Hilbert transform, domain remains the same, signals are getting changed. How? We will see it afterwards. This is second point. Third point, Hilbert transform, what it does, it will shift the signal by minus 90 degree. This is what the basic definition says. Okay, the definition I will take it afterwards, but as of now, the first point is domain will not get changed. Domain will not get changed. Second point, there will be change in the signal itself. Third point, what it does is, it will shift the signal by minus 90 degree. So how it does, we will see it in a few seconds. So it will shift the signal by minus 90 degrees. And the fourth point which is important is, if I'm telling it is from time domain to time domain, so how can I get the frequency domain of the domain of this Hilbert transform? So to get the frequency domain, I have to apply the Fourier transform to the converted signal. So what they say that if we multiply positive spectrum of x of t, sorry, positive frequency. So if we multiply positive frequency of signal, I will say x of t, by minus j, then and negative frequency of x of t by plus j, then I can convert the Hilbert transformed signal, Hilbert transform of x of t into its Fourier transform. So to convert the Hilbert transformed signal into its Fourier, what should I do? I should go for multiplying minus j to the positive frequencies plus j to the negative frequencies. So this is the fourth point. So first point, domain will not get changed. Second point, there will be change in the signal. How it will get changed, we will see it. Third point, Hilbert transform is going to shift the phase of the signal by minus 90 degree. And the fourth point, if I want to convert into its frequency domain, then I have to multiply minus j to all the positive frequencies and plus j to all the negative frequencies. Then I can convert into Fourier transform. So this is a basic. So we'll come to the definition now. So as defined in the frequency transform or a Fourier transform was a frequency selective. Here the Hilbert transform is a phase selective. What it means, I'm going to change the phases. They used to get the frequencies. Here I'm going to deal with the phase. So definition goes like this: when the phase angles of all the components of a given signal are shifted by plus or minus 90 degree, the resulting function of a time is known as Hilbert transform of the signal. It is also called as quadrature filter. So we'll see it. We'll see this part afterwards. First, let us understand this. Just for your understanding sake, I'll just take one signal. So what it says that when the phase angles of all the components of the given signal is shifted by plus or minus 90 degree. So all the components means these all components, each and every component of the signal. So this each and every component of the signal are shifted. They are getting shifted. All the components, I will take all the components, are getting shifted by plus or minus 90 degree. So shifting by plus or minus 90 degree. If I shift all the frequency component of this signal by plus or minus 90 degree, then the resulting signal, whatever the result signal I will get it, whatever I am going to get it, is the Hilbert transform of the original signal. So this is what it means. Next question arises, why it is called as a quadrature filter? So what do you mean by quadrature? I'll give another example. Say I have two signals. We already seen these kind of signals. What kind of signal is this? This is and cosine wave or cos wave. Cosine wave or cos wave. And another one is what kind of signal is this? This is sine. wave. If you look at this, what is the phase difference of this? You already seen such kind of signals. It is 90 degree. Whenever two signals are with the phase difference of 90 degree, then these two signals are called as quadrature signals. Quadrature signals. So what we are doing in this Hilbert transform, we are going to shifting the signal by plus or minus 90 degree. That's why the quadrature filter is used. Filter, it is going to, we'll say it afterwards. So quadrature, the meaning of the quadrature is, as we are shifting it by plus or minus 90 degree, those signals, the resulting signal with respect to the previous signal is nothing but they are both are in quadrature to each other. So this is definition of the Hilbert transform. So after dealing with the definition, let us start with the derivation. So derivation goes like this. That means it's not a derivation, just a set of equations which are present. So let us consider a signal g of t. There is one signal which is a g of t. I am going to consider this signal as a real valued signal. Real valued signal. So question arises, what do you mean by real valued signal? So you go to the little bit of this, about this. I'll take a new page. So I'll take a frequency Fourier transform of a signal. If this is like this, the Fourier transform of some signal is like this, that is centered at 0 and it is symmetric, that is from 0 minus w, and this side also it is 0 to w, both are symmetric. If the signal is of this kind, the Fourier transform of signal is this kind, then it is called as real valued signal. And another one comes, which we'll come across later in this chapter, that is complex valued signal. So what do you mean complex valued signal? The frequency content will be there, but this will not be symmetric. Say it will be minus w2 by 2 and this is 3w2 by 2. Both are not symmetric. These kind of signals are called as complex valued signal. So what we are considering in the Hilbert transform, we are considering the signal which you are dealing with is the real valued signal. That means the spectrum of that is completely symmetric. So after seeing this, let us continue with this real valued signal, and its Fourier transform is g of f. The Hilbert transform of g of t, which we denote it by g cap of t. So this is the notation which you are going to use it for the Hilbert transform, is defined as g cap of t is equal to 1 by pi integration from minus infinity to plus infinity g of tau divided by t minus tau d tau. So I'll call this equation as 1. So when I look at this equation, I'll say that the Hilbert transform equation is a linear operation. Now question arises, what do you mean a linear operation? Linear, you already studied the linear signal, check whether the signal is given is linear or no. So for that, so what I will do is, if you already learned all these things, linearity of the signal and all, if you remember the differentiation signal, that is differentiation of f of x plus g of x is equal to d by dx of f of x plus d by dx of g of x. What it means? If I add these two and afterwards I differentiate, whatever the result I am going to get it, I will call it as a1. And if I separately differentiate them and then add them, I'll call this as a2. If these two are equal, then I'm going to call it as linear. As we know, already studied this in signals and system, the differentiation is a linear operation. When I say differentiation is a linear operation, I can say integration is also a linear operation. When I say integration is a linear operation, that means the Hilbert transform is also a linear operation. So once we already defined the Hilbert transform equation, let us define the inverse Hilbert transform equation. So the inverse Hilbert transform is given by g of t is equal to minus 1 by pi integration minus infinity to plus infinity g cap of tau divided by t minus tau into d tau. I'll call this equation as 2. And after saying this, what I'm going to say is this g of t and g of t is Hilbert transform pair. So these kind of some pairs you're going to see it in the example. What you already seen Fourier transform pairs like that. G of t and g cap of t as Hilbert transform pairs. So you already we defined g of t and g cap of t, the Hilbert transform, inverse and inverse Hilbert transform. Okay, now what I say is, okay, let me look at the first equation, that is this one. If I look at the equation, can you recall what kind of equation you already seen this equation in your signal systems? So the equation, what kind of equation is this? It is a convolution or integral convolution. So what I am saying is, if you look at the equation 1, we can say that g cap of t is a convolution of g of t with the time function some pi t. Okay, what do you mean a convolution? I'm just going to give a brief introduction about that. So convolution is nothing but, it is if I take two signals, one is f of t is convolved with g of t. Just for your sake, I'm just giving this equation. It is minus infinity to plus infinity f of tau into g of t minus tau d tau, or you can write it like this also, g minus t to plus infinity g of tau into f of t minus tau d tau. Both are true. So if I look at this first equation, that is this one, it is of that kind, g of tau into 1 by t minus tau. Same here, f of tau into g of t minus tau. So I'm telling it is a convolution between g of t and time function 1 by pi t. Let me see whether it is true or no. So let me call this 1 by pi t as h of t, some function h of t. So what I can write is, from 1, g cap of t is equal to, what I am telling, it is a convolution of g of t with the time function pi of t, 1 by pi t. So g of t is convolved with h of t. I'll call this equation as 3. So what is g of t? I don't know. I'll keep it as it is. What is h of t? It is already defined. It is 1 by pi t. So 1 by pi t, I will write it here. So 1 by pi t is a constant. I will take it out. So if I apply the convolution, it's minus infinity to plus infinity as I defined here. So it will be g of tau into 1 by t minus tau. Pi is a constant which I have taken out. What is left out is 1 by t. So it will be t minus tau d tau. So if I club this 2, it will become g cap of t is equal to 1 by pi minus infinity to plus infinity g of tau divided by t minus tau d tau. It is same as your equation number 1. So now can I, what I just told here in the above statement, can I say that it is a convolution between g of t and the pi, 1 by pi t? Yes, I can, because when I consider like that, when I convert these two signals, what I'm getting the signal which is defined in equation number 1. So this equation I'm going to call it as equation number 4. So let me continue with this. So I already defined the equation for the Hilbert transform. I'll apply the Fourier transform to the equation number 3. What is equation number 3 here? The equation number 3 is g cap of t is equal to g of t convolved with h of t. So what will be, if I apply the Fourier transform to the convolution, what will happen? In the time domain, if it is a convolution, in the frequency domain it will be the multiplication. You already know this. So g cap of f is equal to g of f into h of f. G cap of f as it is, g of f as it is, h of f. So if I apply the Fourier transform for this 1 by pi t, I'm going to get it as minus j signum of f. This particular thing I'm going to leave it for you as exercise, that is find the Fourier transform of 1 by pi t. This is for, if you want you can just do it. You're going to get minus j signum of f. Just try it out. So let me continue. So just rearrange the terms. The g cap of f is equal to minus j signum of f into g of f. This I'll call it as phi. Now question is, what is signum of f? Again, this you already seen the signal in the signal systems. So signum of f, where it is, the signum of f is defined as 1 for the positive frequencies, 0 for 0, minus 1 for the negative frequencies. So this is the signum function. So how it looks like? So if I draw it, so what they are doing, this is the f, this is my signum of f. So for positive frequencies, that is from 0 to plus infinity, it is 1. So and for negative frequency it is minus 1. So this is how the signum function looks like. This also you already studied. Please go through your previous studies in the signal systems. So this is my signum. This is the Fourier transform of the Hilbert transform g cap of t. So when I look at this, I am, as I already told, that my Hilbert transform is a linear function, or it is called as linear operation. Okay, so and now I am telling that the signum, what you are going to get is, there is a LTI system. What is this? Linear time invariant system. So from this phi equation, what I can say that there is a signal, there is an input signal g of f. I want to get the output as g cap of f. So it has to pass through some function, some system. So that system I'm going to call it as LTI, linear time invariant system, whose transform function is minus j signum of f. Whose transfer function is minus j signum of f. So the input of this is g of t or g of f. The output is g cap of t or g cap of f. So when I pass this g of f or g of t through the LTI system, whose transform function is h of f is equal to minus j signum of f, I am going to get it g cap of f. So I am just drawn a diagram for this equation number 5. So this is what we are what the diagram is. Now next, so this is LCI system. Maybe what I can say that this particular thing, this LTI system is providing this, what I am telling, plus or minus 90 degree phase shift. This may be the system which is providing the plus or minus 90 degree. Then only the signals are getting changed by change its phase. There is nothing else except this particular part. So what I'm assuming that this particular part only is going to change my phase. So that's what I wrote. So this LTI system may provide plus or minus 90 degree phase shift to the input signal. So therefore we can say that when all positive frequencies of input are given, then the output is shifted by minus 90 degree, and when all negative frequencies of input are given, then output is shifted by plus 90 degree. This I am telling. This also I told you at the beginning, the fourth point. If you recall it, the fourth point which I explained here. So now I'll explain how it is true. So how can you say this? So I'll take this from 6. What is the sixth equation? So my sixth equation is the signum function. So from 6, what I'm going to do is signum function, I will take it here, but LTI, our LTI system is minus j signum of f. So if I just multiply this minus j to this, so minus j into 1 minus j into minus 1. So it will be minus j for positive frequencies, minus j into minus 1, it is plus j for negative frequencies. That's what I told at the beginning. I'm going to multiply minus j to the positive frequencies plus j to the negative frequencies. So minus j means I'm going to shift the signal by the minus 90, plus j means this is minus 90, plus j means I'm going to shift the signal by plus 90. So what I'm going to do, just from this Hilbert transform, the phase is getting shifted the positive frequencies are getting shifted by the minus 90 degree and the negative frequency are getting shifted by the plus 90 degree. But remember, the amplitude is not getting changed. It is unaltered or unaffected. So the amplitude of this will be flat. So let me draw the phase and amplitude response of this signal. So what I'm telling, so as I told, the positive frequency, the angle is minus 90 degree, and for the negative frequency the angle is plus 90 degree. So it's argument of h of f. The phase diagram is this, or phase response, and the amplitude response, as I told, it is unaffected, so it will be flat throughout 1.0. so the amplitude response is flat. So this is my amplitude response of response. So this completes the Hilbert transform. So what we studied the equation of the Hilbert transform. First we discussed some of the part of the Fourier transform, and then we went for some of the assumption or some of the basics of the Hilbert transform. In that we studied that it is not going to change the domain, it is going to change the signal. And then we started with the equation, and then we derived its Fourier transform, and lastly we ended with how it is going to shift. For the positive frequency it is going to shift it by minus 90 degree, and for the negative frequency it is going to shift it by plus 90 degree. So when I shift it by plus or minus 90 degree, obviously the signal is going to change. For example, if I'll take an example. Say I have the cos signal or one signal. Okay, I'll call this signal as cos theta. Okay, I'll not make it very complex. So if I go for shifting of this from minus 90 degree, that is cos theta minus 90. So what I'm going to get it? Simple trigonometry. It's a sine theta. So my signal was cos theta. By applying the Hilbert transform, I'm getting sine theta. The signal is getting changed, but the domain remains the same. Instead of theta, if I take as 2 pi ft, it's a common notation we already used to see. So the signal is getting changed from cos signal to it is changing to the sine signal. This is what the Hilbert transform does. Thank you. In the next class, we're going to discuss the properties of Hilbert transform. If you have any queries, please comment, or my WhatsApp number is 9164191087. I'm going to give this number in the description also. Please, if you have any queries or any questions, anything, please comment in the YouTube in this video, or you can just ask me in the WhatsApp also. Thank you.